Hello, welcome back to three-phase circuit analysis. We're covering delta Y circuit problems. This is the part one, the first problem that we're going to cover in our sequence. It's a really good problem because it's very practical. It's very representative of what you might actually see on an exam. So let's take a look at what we have. First of all, you have this circuit diagram, which looks a little bit weird. We'll talk about it a little bit more in a second. But believe it or not, this is actually a delta source is what this is. You know it's a source because you see you have three sources, so you know you have three phases. You have three impedances. You have an impedance associated with this source, an impedance associated with this source, and an impedance associated with this source. You notice that all three of these impedances are the same, so you have 2.7 ohms for the real part, and the inductive part is 13.5 ohms. So because they're all the same, you know it's a balanced source. Now you look at the impedances are balanced anyway, and then you look at the sources themselves. 4156 is the magnitude in all three cases, and then you have 0 degrees and you have the plus minus 120 there. So because you have all three phases of the source impedances the same, and because the source voltages have the same magnitude but their phases are just different by 120, then you have a balanced three-phase source. You know that this is not a Y source because a Y source looks very different than this. I mean, even if you don't draw it as an actual Y, there's always a central point in a Y source that's the neutral terminal. So whether or not it's flattened or whatever, you can always tell very easily if it's a Y source. But in here, there is no central point, really. I mean, you might think this is a central point, but this central point doesn't touch this source at all. This is connected over to the outside. So I'm going to prove it to you in a second, but this is a flattened out delta source. Right? So typically when you draw a delta source, not always, but typically you'll draw it like this. You will sometimes draw it in a triangle fashion. That's fine. But sometimes I'll try to trip you up and draw it like this. So this is a delta source. And then it tells us that this delta source is connected to a Y load. So we have a delta source. We have not drawn it, but it's connected to a Y load. The line impedance, here we have the three lines, A, B, and C. The line impedance is 9.1 plus J 71.56 ohms per phase. That's just giving you the line impedance of all three phases without drawing the lines. And it says it's connected to a load, and each phase of the load is 1910 minus J 636 ohms. So you can see that the load actually is a capacitive component because of the negative sign. And we have the real part here as well. So you have this delta source. It's connected, the three transmission lines are connected to the same line impedance which is given here. And then on the other side, which we haven't drawn, we have a Y connected load, which would be, we could draw it all, but what the point is that you're not always going to have it drawn for you. In fact, a lot of times you won't. It'll just give you some information, they'll tell you something else about the loads and the lines, and you'll just have to kind of use what you have. Of course, we could draw this, and we could draw the Y load. That would be fine. But in this particular case, we don't need to. Now let's take a look at what we're actually asked to find. First step is draw a single-phase equivalent circuit. Okay, we know how to do that. We'll do it in a second. And we want to find the magnitude of the line voltage at the load terminals. Now you see why terminology is so important. Magnitude means we don't care about the phase angle of whatever it is we're asked to find. And we're trying to find the line voltage, which means what? Line-to-line voltage, so VAB for instance. But at the load terminals. Now we haven't even drawn the load, so you have to use your imagination or you draw it yourself on your paper. But anyway, you have this delta source is connected to a load. You're going to have an A, B, and a C terminal. So what this is asking you to do is you want to find that line voltage, VAB, right? But the magnitude only of it, right? So that's what we're trying to find for part B. Part C, find the magnitude of the phase current in the delta source. So this is a delta source, and we want to find the magnitude of the phase current. So remember, what's the phase current? It's the current going through each branch of that triangle in the delta, because that's each phase is one of the legs of the triangle, so we want to find what the current is through each leg of that triangle. Now this triangle's flattened, and I'll explain why in a second, but basically you're asked to find, this would be a phase current through one of the phases, this would be a phase current through another phase, and this one through here would be a phase current through the third phase. So you're trying to find the phase current. In this case, it tells you only want the magnitude. So when you're asked to find the magnitude, you don't have to find A, B, and C phases because all the magnitudes are going to be the same for the line currents and the phase currents. So you just have to find the magnitude for one of them, and that's going to be the same magnitude as the other two. Finally, we want to find the magnitude of the line voltage at the source terminals. So just like we found the line voltage at the load, now we're asked to find the line voltage at the source. So this one's actually drawn here since we have the source. The line voltage, which is another way of saying line-to-line voltage, would be, for instance, VAB. or V little a little b, which I have drawn as capital A, B, and C, telling you they're connected to the loads here. But between, for instance, A and B, or B and C, or C and A. So I just want to kind of go through what we're asked to find, but we're going to talk about it in a lot more detail as we go. Now, the first thing that we want to do is I want to prove to you that this is actually a flattened triangle, because when you might want to convince yourself of that. So before we actually look at what we have on the board, let's draw what we know a delta source to look like. So we'll have some A terminal, and then there's going to be a triangle, right? There's going to be some impedance. I'm going to write it as a triangle, a rectangle here. And there's going to be some source associated with that A phase, or with this phase here. And then you're going to come here, and then you're going to have another leg of the triangle, which will have another impedance and another source. And you're going to have another leg of the triangle with a source and an impedance. These are the kinds of drawings that we've done in previous lessons, so I'm just kind of showing you here. We're labeling this C, and we're labeling this lowercase b. And so the way we do this is we say this is a line that goes this way, this is a line that goes this way, and from the C terminal we drag it down and we bring it over. So you should be able to convince yourself. I mean, I haven't drawn the plus minus in here, I haven't drawn what is inside these boxes, but you know each leg of the triangle has an impedance, and each leg of the triangle has a source. And there's three of them because they're three phases and they're arranged in a triangle like this. Okay, so you have A, C, and B. So you need to remember that. Follow me up here. Here's A up here. So this is the terminal lowercase a. That's the tip of the triangle. So between A and B is this leg of the triangle. So if we go back up here, that would be this leg here between A and B that has an impedance here, and it also has a source. And now we've come to point lowercase b, which is here. Then you go B this direction. You go from B to C. So this is going from B to C. And again, you have an impedance and you have a source. And then continuing on from C, you go back around connected to A, and here from C you're connecting yourself back around to A, again through a source and through a impedance. So even though the top part doesn't look like a triangle, it is a triangle because you start with A, and if you trace out your fingers from the A terminal, you should go and hit a C and you should hit a B. So if we start from A, we trace this way, we should hit a C, which we do, and we should hit a B, which we do, and then once we get there, those two are connected through the base of the triangle. So really, if you want to picture this in your head, if you kind of grab this with your hands and kind of rotate it and angle it like part of a triangle, this is the left-hand side of the triangle. You take this top part, pull it out as the second part of the triangle, and then the bottom of those two are connected through this right here. That's how you read that. So the left-hand side is the left-hand slant of the triangle. This guy right here, this little part, is the right-hand side of the triangle, and then the bottoms of those two are connected through this, which is the base of the triangle. I wanted to do that for you to prove it to you because it's not obvious at first that that is an actual delta source, and a lot of times you will have it drawn like this and they won't even tell you it's a delta source. In fact, I didn't actually tell you this is a delta source in this problem at all. I just said this source is connected to a Y load, and you have to know that that's a delta source. So that's why I went through the exercise with you. Okay, part A is asking us to draw a single phase equivalent circuit. Now, the way that you do that for any of these problems is you have to get the source into a Y configuration, and you have to get the load into a Y configuration. But in this case, we're already told that this source is already connected to a Y load. So we know that the load is already taken care of. It's already a Y connected load. We don't have to do any transformation for that. But the source is delta. So let's go ahead and convert this source into an equivalent Y source. It means we have to find the equivalent impedance of each leg in terms of its Y counterpart, and we also have to transform the sources appropriately as well. So let's go and do that. I've already given the equations for that in the previous section, so what we need to do for part A is we need to transform the delta source. So what we say is Zy, this is the Y equivalent impedance for each leg of the new Y source we're constructing, is going to be whatever impedance is in one of these legs of the triangle divided by 3. And then we go over here and we see each leg of the triangle is 2.7 plus J13.5. 2.7 plus J13.5, we divide that by 3. And so what we get for Z sub Y is 0.9 plus J 4.5 ohms. So what this means is if we were to take this delta source and construct an equivalent Y source, then in the equivalent Y, which has a neutral terminal, comes down and it splits into a Y, or you can think of it as coming together in a Y and coming down. Each leg is going to have an impedance that's calculated by this right here. Now what we need to do is figure out what would be the source that we would need to put in each leg of that Y equivalent circuit. And to find the source, it's a similar procedure. Not exact, but it's similar. So we say the source for the equivalent Y circuit is 1 over the square root of 3 times the source voltage for the delta source. This is what we're converting from. And then we have to go and we have to shift this guy by either minus or plus 30 degrees. Now, anytime you see minus plus or plus minus, what you do is you choose the top sign if it's a positive phase sequence or the bottom sign if it's a negative phase sequence. So we need to know what the phase sequence of this problem is. Now, the phase sequence wasn't given to you. I didn't tell you, hey, this delta source is a positive phase sequence. I never told you that. If you come over here and look, all you're given is a drawing. You're told that it's connected to some transmission lines, which is connected to a load, and you're asked to find some stuff. So how do you actually go about finding the phase sequence? Well, you're given each of the sources. You know this is 0, and you know this is 120, and you know this is negative 120. So you have the phases of all of the sources, so you can obviously figure out the phase sequence. But you need to resist the urge to just kind of look at the drawing and say, oh yeah, that's positive phase sequence, because you'll probably make a mistake eventually. So what you really need to do is draw our little diagram. So what we have here is we're going to end up having, kind of have to draw it small, I apologize for that. But what we have is we have our phasor diagram here. Now, one of these is going to be A, one of these is going to be B, and one of these is going to be C. And then once we label it all, we'll be able to read the phase sequence directly off the diagram. So the first thing we do is we say, what is the source in this drawing associated with the A phase? Remember what the A phase is, right? It means it's the voltage source between A and B, right? That would be what we call the A phase source. The voltage source that's between B and C is the B source, and the voltage source between C and back up to A again, that's what we call the C source. So for the A source, that's what's going between A and B. You see that one has the phase angle of 0 degrees. So that means that's this arrow right here. So we're going to label this A, because we have to look at the drawing and figure out what is the source between A and B. That's the A phase, and that's at 0 degrees, so we label it there. One of them has to be 0. Actually, one of them doesn't have to be a 0. You don't have to have one of these phases at 0. As long as they all separate by 120, it's valid. It's just usually one of these 3 phases will be a 0 phase reference. Okay. Then you look over here and you say, well, what is what we call the B phase is what is in between B and C. And you see that that's this one right here. And that's at positive 120 degrees, which means this is the B phase right here. So we put a B right here, and we put a little diagram to help me remember, even though it's already in the drawing, that this is 120 degrees gets me from A to B. And then you look over here and you say the C phase is whatever is between A and C, and that's negative 120. So this is the C phase, and then you can remind yourself that this is negative 120. Now when you look at this, this is ACB phase sequence, ACB, which is a negative phase sequence. So this is a negative phase sequence. So because of that, we're actually going to say it's a negative phase sequence. So because of that, we're going to choose the bottom sign. So this would be a positive phase sequence, we choose this. Negative phase sequence, we choose that. And so because of that, we say the source for the equivalent Y is 1 over square root of 3 times the voltage source that we are given in this problem statement. Now, what we want to do is we want to find ultimately a single phase equivalent circuit. So that means typically what you'll do is you'll just look at the A phase. You'll find out what is the equivalent voltage source for the A phase, so that when you draw your single phase equivalent circuit, you're almost always doing it for the A phase, right? So that's why I'm going to say the A phase is this source right here, 4156 angle of 0. That's what I'm going to stick in here, 4156 angle 0, okay? And then it's going to be 1 at an angle of positive 30, because we're choosing the bottom sign, so we're basically multiplying by a phasor, which is magnitude 1, which is implied here, positive 30 degrees. So what we figured out from all of this stuff is that the source, the equivalent Y source there, is going to be this guy divided by square root of 3, and we're going to be adding 30 degrees to it. So what we're going to get is 2399.47 angle, we're adding these phases, so we get 30 degrees. And this is for the A phase. If we were doing a single phase equivalent for the B phase or the C phase, we would have put one of the other sources in here, and everything would be the same except for the phase would be different. But for single phase equivalent, we just do it for the A phase. So, and obviously you could round this to 2400, that's fine. I'm just keeping some extra accuracy there. So what we have now is we have an equivalent Y source that if we built it for all three phases and we put it in a black box, and if each of these Y legs of the source had this impedance, and for the A phase, if we had this as a source, and then the B phase and the C phase, of course, we would have different, because it's a negative phase sequence, we would go when we find the B phase and the C phase by adding or subtracting 120 degrees from that. And if we built that as a Y source, we put it in a box with three terminals sticking out, A, B, and C. And then if we compared it to this thing, which is a totally different source, totally different impedances, but just with three wires, A, B, and C sticking out, then those two would behave exactly the same. From a terminal point of view, they would behave exactly the same. So just to recap, we've taken our delta source, we've calculated the equivalent Y source in each leg of the equivalent Y source, and we've also calculated the equivalent impedance and an equivalent Y impedance if we transform that delta source to a Y source. So we're going to use these two pieces of information, pretend that we could build this delta source as if it were a Y source, and we're going to do that for the purpose of writing down our single phase equivalent circuit. So every single phase equivalent circuit has some source, right? We'll label everything in a second. Every single phase equivalent circuit has some source impedance. This is a resistive part of that impedance and an inductive part of that impedance. And then the single phase equivalent circuit has a resistive line impedance and a resistive line, resistance inductance usually, so some sort of line impedance, right? And then of course the single phase equivalent circuit has the resistive part of the load impedance and the inductive part, or whatever you have. In this case, actually, we go back to our problem statement. Our load impedance is actually capacitive because we have a minus sign there. So it's incorrect to write it as an inductor. So let's go ahead and write it as we have been given. We know it's capacitive, so let's go ahead and write it that way. And then we're going to connect this back around. So in order to write down a single phase equivalent circuit, you need to have your source modeled as a Y source and your load as a Y load. So as typical, we're going to go ahead and label everything in this drawing and have it as a reference to use in solving our problems. Now this is terminal what we call little a. And this is terminal what we call capital A. Source, line, load. Okay? Now on the load side, remember there's three phases, so they're connected in a Y. This is the common terminal where all three phases come together. We call that capital N, like this. And then over here on the source side, remember we're modeling this as if it were a Y source. So we have a lowercase n over here where the other phases of this Y source are connected to a common point. Now it's important to note that this is a single phase equivalent diagram. So there is no neutral terminal like this, no common terminal. In the actual, when we go over here to our delta source, the actual delta source, you might say this is a common terminal, but this terminal is not connected to this source at all. So there is no common point in a triangle, right? But once we take this, we model it as a Y source, then we can say that this equivalent Y source has this neutral terminal. So you need to kind of keep in mind that this isn't, this is true, this neutral terminal is true if we had built it as a Y source, but in reality we have a delta source, so we don't have it. But we can use this fact, we can use the idea of a neutral terminal in this equivalent source as if it were real to do calculations. That's the power of using this method. So let's go ahead and label everything. We have all the information now. So the source voltage is going to be 2399.47 at an angle of 30 degrees. And we'll switch colors just to mix things up a little bit. The source impedance, right, which is this guy right here, Z is 0.9 and 4.5. So this is 0.9 ohms and 4.5 ohms. And then we go back over here, we have a line impedance of 9.1 J71.56. So this is 9.1 ohms, J71.56 ohms. And then the load impedance for all three is 1910 for the real part, negative J636. So we'll say 1910 ohms, and I'm going to write it on this side, negative J636 ohms. So this is what you would circle on your exam as the single phase equivalent circuit for this circuit. We take the delta source, we transform it to a Y source, The load is already in terms of a Y load, so now we have YY, and then we just write it down. That's all we do. Now, why are we doing all this stuff? Because we go over here to part B, and we're asked, find the magnitude, that's all we care about, of the line voltage at the load terminals, the line voltage. So remember, what we have here is you're kind of at this point, once you have transformed the source into a Y source and you've drawn the single phase equivalent circuit, now you start using all of the knowledge that we have done in all the other problems, the YY problems that we've done a lot of, in order to basically solve the rest of the problem. There's some things to think about as we go along, but essentially you're using all of that knowledge that we have already learned in the past. That's why we spent so much time on YY circuits. So the thing you know about the single phase equivalent circuit, even though the problem doesn't actually ask you for it, you know that you have some kind of current circulating this direction, and we call that I, little a, big A, because it's going from source to load, little a to big A. We know what that is. And what we want to do is we want to figure out the line voltage. We want the magnitude, but ultimately we want the line voltage. Okay, so you need to ask yourself, what can I find? Well, I know this voltage, I know all the impedances, so I know how to find IAA. I know how to find the current circulating in this single phase, in the A phase, basically. Once I know that, I am able to, with Ohm's law, calculate the voltage drop across this load, this A phase load, from A to N, right? That is not the line-to-line voltage, though. That's the line-to-neutral voltage. But once I have that, we already know that whenever I need to shift voltages around, in this case line to neutral going to line, I use the voltage shift formula. So our strategy here is to basically first find the current circulating in the A phase, then find the line to neutral voltage, then shift that voltage to find the line voltage, and then just take the magnitude of the answer because that's all they're asking us to do. So that's exactly what we're going to do. Let me see how many pages I have left here. Yeah, I think I have... yeah, I think I have enough room to kind of continue on this side. So in order to find this current I sub AA, right, little a, big A, what is that going to be? It's going to be, let me flip back a little bit, it's going to be voltage over the total impedance. So what you're going to have is 2399.47 at an angle of 30. And you're going to divide that by the sum of all of these things. So I'm just going to write it down explicitly, but in your calculator you can just dump it all in. 0.9 and 4.5 plus J 4.5. And you're going to add to that in the line, which is this guy right here, 9.1 plus J 71.56. And then here you have 1910 minus J 636 from the capacitive part. Okay, so you have a complex number on the top as a polar phasor. You have a bunch of complex numbers on the bottom as rectangular phasors. So you can stick all that stuff in your calculator and divide, or if you really want to hurt yourself, you can do it all by hand, but I recommend using a calculator. And what you're going to get is 1.2 magnitude at an angle of 46.26 degrees amps. Of course, it's all RMS. Everything's RMS in all of these problems. So we found the current circulating. Now, you got to remember, this is a single phase equivalent. So what this means is this is my real source, okay? So that means the current coming out of this leg here in the A phase going toward the line, that is what the current is over here. I've modeled this as a Y source, so this stuff didn't even enter into the calculation other than its transformed version over there. But if I put this in a black box, and I can model it as something else, and so I've calculated the real current coming out. So the current circulating here is what I've found, IAA, from A going this direction. That's what I found. So that's the current. Now the next part of the puzzle is, let's figure out what voltage between here and here is. So I is equal to, or V is equal to IR. We have the current times the impedance. I call it IR, but it's IZ, the impedance. So current times impedance, that's going to give us that voltage there. And so that's what we're going to do next. So we label it V capital A capital N is going to be the current we just found, 1.20 angle 46.26. And we're going to multiply that by 1910 minus J 636. So V capital A N is going to then equal 241573 angle 2784 volts RMS. Everything's RMS. So, you know, if you're not paying attention, you'll circle this as your answer, saying, oh, that's the answer, it's the voltage. But when you look carefully, it says the line voltage. What we calculated there, that's the phase voltage. That's the voltage across this A phase. We don't want that. We want from A to B, the adjacent line, AB. That's what the line voltage is, the voltage between the lines. And we've already learned that in three-phase circuits, when we need to convert between line to neutral, line to line voltages, we have a formula to do that. We have an equation to do that we've derived in the past. And that equation is the following. So we're going to shift VAN to VAB because we want line to line voltage. And how do we do that? We say V capital AB is equal to the square root of 3 times V capital AN. And then we have to choose plus or minus 30-degree phase shift. And we choose this sign based on our problem. Now our problem here, we've already gone through it. We've drawn our diagram. The phase sequence is ACB, which is a negative phase sequence. Negative phase sequence means we choose the bottom one of these. So instead of writing it again, I'm just going to erase that. And so we actually have a phase shift of negative 30 degrees in our particular problem. So for our particular problem, VAB, capital AB, is square root of 3 times what we have over here is the 2415, 73 at an angle of 2784. And then we have this phase shift here. So you can write it as 1 at an angle of negative 30, or you could just leave the 1 off. It doesn't matter. What you're going to do is multiply these magnitudes, and you're going to be adding these phases. Of course, you can do it in your calculator, but that's what your calculator is going to be doing. So I'll switch colors for our final answer here. VAB, we do all that stuff. We get 4184.17 at an angle of negative 2.16. Notice when you subtract these, you get around negative 2. So that's what it is. Now our problem, we actually had enough information to find the full-blown phasor, AB, right? The line-to-line voltage. But our problem didn't ask for that. Our problem asked for the magnitude of the line voltage. Magnitude is just what sits out in front here. So we say magnitude VAB is equal to 4184.17 volts RMS. And that is my advice. Anytime a problem says, a lot of students will get confused when they see something that's like, find the magnitude of something. Then they start thinking, well, I don't care about the phase, I just care about the magnitude. So I'll just start using magnitudes. I'll multiply by magnitudes. But that gets you into trouble because if you start using magnitude only too early in the problem statement, throwing away the phase information too early on, then you're going to get erroneous answers. I don't have time or really inclination to go examples why, but ultimately what you want to do for any problem that asks you for the magnitude of something, don't start at the beginning just trying to find the magnitude. What you do is you always try to deal with the full-blown phasors, as much information as you have. Try to solve the problem in terms of its full phasor value if you can, and then strip the magnitude out of the answer. If you start doing things like throwing away this phase here, because you might look at this and say, oh, I don't care about the phase, I just care about the magnitude, or you might go even earlier than that. Well, in this particular case, it doesn't much matter. But if you were to go back over here to when you were calculating the current here and throwing away information too early and then carrying that through and rippling it through other problems, basically what I'm trying to say is phase information is important, and you can't throw it away. If your problem asks you only for magnitude, then it was probably constructed in such a way that you have enough information to get from point A to point B without throwing away anything important. But the way to deal with it as a student doing these problems, instead of trying to figure out what you can throw away or what you can't, is just try to work the problem in its full-blown phasor glory as far as you can, and then get the phase information at the end, or get the magnitude information at the end. Okay, which is what we did here. So that's what I wanted to show you. So that's the magnitude, 4184.17 volts RMS. Now the next part of the problem is interesting. It says find the magnitude, again, all of these are magnitudes, of the phase current in the delta source. So this one's a little bit different because we want the phase current. So first of all, you have to know what a phase current is. Phase current is a current, or the current, flowing through the A phase. But it tells you we want to find the phase current going through the delta source. So what you basically are thinking about, this is your triangle representation of this delta source. So you want the current that's flowing here in this leg between A and B, because that's the current through the A phase, right? It has to be one of these three, right? So it's the one going between, in between here terminals B and terminals A. Okay? How do we find that? So you have to figure out a method or a strategy to inch your way to that answer. And so the way we're going to do that is we're going to say, well, we know what the current is circulating around here, right? And much like on the other side, we were able to figure out what this voltage drop was and then shift it to get VAB. What we're going to do now is we're going to go figure out what is the current circulating through the source. Basically, we know this current. This is a current that's going through the line, and also, of course, it goes through the load and it goes back around, but it's a line current, right? That's what it is. We know how to shift for a delta source or a delta load. The line current is different than the phase current. You can see that because of this triangle arrangement here. This is what a delta source looks like. We know what this is. We just found this. This current is I little a big A. It's coming out of this terminal going this direction. That's what it is. We just found it over there. What we will do is we want to use this and shift it to figure out what is the equivalent current flowing through this leg of the triangle. And we do that with the current shift formula. So there's really only two formulas in three-phase circuits. There's the voltage shift formula. Sometimes when the voltages between line and phase are different, you have to shift. And then there's the current shift formula. In this case, we're going to use the current shift formula to figure out, we know the line current, we're going to shift and figure out what the phase current is. And we've already talked about what that equation is. We're going to shift. And we're going to shift between what? We know I little a big A. That's the line current. And we're going to shift that to be that leg in the triangle. But the only little wrinkle is, normally, if it were a load over here, we would be shifting to AB, right? That's the leg of the triangle between terminals A and B. But for sources, we already talked about these little, it's really a labeling thing, but we don't call it AB, we call it BA. The reason it's flipped around, just to recap, is because these are sources, so the current's actually coming this direction out of the source, so it's really between B, going from B to A, like this. So the way you think about it in your head is, we know it has to go between terminals A and B, but since it's a source, we flip it around. It's just a notation issue. We're going from this to this. This is a line current, this is a phase current. So what's the equation that governs that? In general, it's line current is equal to square root of 3 times the phase current. And then we shift it by a phase angle of either negative or positive 30 degrees. And we have to pick which one. So in this particular case, line current is IAA is equal to square root of 3 times the phase current, which is IBA. This is the current in the source that it corresponds or is a partner with this A phase line current. And then we're going to shift it by either plus or minus 30 degrees, but since we know it's a negative phase sequence, we're going to choose the bottom, which is positive 30 degrees, like this. So now we just have to write, we wrote the equation down, now we plug in what we know. We know this, and we're trying to find this. So let's go ahead and stick, what do we know for IAA? It's 1.2 at this angle. So what we do is we say 1.2 at an angle of 46.26, square root of 3, IBA, angle positive 30 degrees. Okay, now what we're going to do is, what you want to do is solve for IBA. So let's go ahead and do that right now. We'll just do a little bit of algebra. IBA is equal to this guy. You know what, let's do it like this. We'll say it's going to be, we're going to move this over here, we're going to move this over here, so it's going to be 1 over the square root of 3 times this phasor, 1.2 at an angle of 46.26, right? And then when we divide by this, of course, you know when you divide by a phasor like this, the magnitude's 1, so that doesn't change, but the phase angle goes negative, so this is going to be angle negative 30. So that's why it changes sign. We've done that many times over. And so now you can say IBA is equal to, when you multiply these things out, you're going to get 0.69 is the magnitude, angle 16.26 degrees, that's amps. And so then from that, because we're asked to only find the magnitude, you say the magnitude of BA is 0.69 amps, RMS, of course. I'm not going to continue writing that forever. All right, so again, what I did is, instead of trying to figure out, oh, they only care about magnitude, I'm only going to see which magnitudes I have and try to deal with that, because I can just promise you that's going to get you into trouble. Eventually, you'll throw away some piece of information too early in the calculation that's going to affect the magnitude of the answer. Instead of doing that, you just see if you can deal with the whole thing in terms of phasor notation. We know the line current in terms of its full phasor. These are just numbers, so of course the answer we get is going to be a full-blown phasor. So then we just do that and we strip off and take the magnitude away. Or we take the phase away and just only, we're left with the magnitude. So that's the magnitude of the current B flowing up to A before it splits again and then it goes off this direction. That's what we have here. Now the last part of the problem is the magnitude of the line voltage at the source terminal. Line voltage at the source terminal. So what does line voltage mean? That's VAB, line to line, VAB, right? But at the source terminal. So that means if you look over here to our, well, depending if you want to look up here or not, VAB is going to be, let's just look down here. It's going to be the voltage across right here. V little a to little a to B. That's what we want to find. How do we find that? Well, we look over here and we say, well, we know the current going through here now, right? We know the current going through here. So we want the voltage VAB. That would be the line voltage at the source terminals. That's a line-to-line voltage, but we only want the magnitude. So let's try to find VAB. So as always, let's go back to our single-phase equivalent circuit and see what we can find to get us there. We know the current circulating here. Now, here's where we get to do something interesting. We know this current, so we are able to find the voltage VAN, the voltage between this terminal just outside the source, A, and the neutral terminal, which remember is kind of fictitious because we just kind of converted to find this source here, this Y source. So the neutral terminal is not really real, but we can model everything as if it is real, as if it were real. We find VAN, the voltage between A and N. If we can find the voltage between VAN, we can just do a voltage shift to find VAB. That's what we've been doing all the time. Pretend I just gave you a problem a long time ago, a YY three-phase circuit problem. If you haven't done those, please go back and do them because it makes all this stuff much easier. In fact, you have to know that stuff to do this stuff. If I gave you this problem as a three-phase YY problem and I gave you this single-phase equivalent circuit, forget about delta loads, forget about delta sources, forget about anything. Just say it was YY. And I said, find the line-to-line voltage at the source. You would say, okay, I know this current, and I know this voltage here, so because of, we'll do the calculations in a second, I can find the voltage drop VAN. That's a line-to-neutral voltage for this Y source, and then I can do a voltage shift to find the line-to-line voltage. We've been doing that forever. That's what you would do. The only difference here is that we've taken our delta source, we're modeling it as a Y source, so this neutral terminal at the source isn't really real, but we can treat it as if it's real. From a modeling perspective, it behaves exactly the same way. That's the thing that blows people's minds at first, that this is an equivalency thing. We can do the problem as if it's real, even though it's not really there, because equivalently, it's exactly the same as our source. So how do we find VAN? That's the question. Well, think about it. You know the voltage here. You could basically, what you would do is you would do a Kirchhoff voltage loop. You would start at the neutral terminal and you'd walk up. If you did this, going through a rise means you count in Kirchhoff voltage loops. This would be a negative because it's a voltage rise. But then this is a drop, a voltage drop across this impedance. The current is going this way, so there would be a voltage drop here. You count that as a positive. And then when you get to the A terminal, you go back down to the source there. And so then you solve those equations, and this would basically be a voltage drop. And then you solve those equations as, or you model it as a voltage. You assume it's a voltage drop, VA to N, right? So you walk in a loop. This is a negative drop. This is a positive drop. And then over here, you're assuming this is a drop, so this is another positive drop. When you do all of that, and then you solve for VAN, let's see here, where is it at? What you're going to get is the following. You're going to get V little a little n is equal to 2399.47. I'm going to write it, and then we're going to make sure you understand it. 30 degrees minus 1.2 angle 4626 multiplied 0.9 plus J 4.5. This is actually crucial to be able to understand the problem here. So this is the source voltage. This is the line current, little a, big A, and this is the line, not the line, the source. The source impedance Z. Okay, remember I said it was like a Kirchhoff voltage loop. So you got to use your imagination here a little bit, but let's pretend for a second that we wrote this down. This would be a negative. If you didn't actually actual Kirchhoff voltage loop, right? Then you would treat this as a negative, so you'd have a negative sign in front of this, positive sign in front of this term, current times impedance, positive, and then you would have this as a positive, VAN. So then when you move these over to the other side, these other terms, and leave VAN on the one side, then everything flips around. The source, which did have a negative in front of it, becomes positive, and this voltage drop across the source impedance, which was positive initially in our drawing, becomes negative. All we did was move the terms to the other side, write a simple little KVL. Why? Because we want to find the voltage between VAN, which now we have. So VAN, take this, multiply that, subtract those two phasor answers, and what you get is 2399.95 at an angle of 29.87 volts. Just like this. So that's the voltage drop. If you were to put a meter here, this is the positive terminal, this is the negative terminal, that's the voltage drop across them. But that's not what we want. We want the line-to-line voltage. We have the line-to-neutral voltage there. So we shift. We say the voltage shift formula is VAB is the square root of 3 times VAN, and we're shifting by either plus or minus 30 degrees, because for voltage shifts we have plus or minus written as plus on top, minus on the bottom, but of course we know it's a negative phase sequence, so we'll take this one away, and it's really going to be a shift like this. So VAB is equal to the square root of 3 times VAN. Let's write the whole phasor down, 2399.95. Whoops, forgot the phase. 29.87. And then we have negative 30 degrees. So then what we have, VAB, let me catch up to myself and just double check everything's correct. 2399, 29.87, negative 30 degrees. Yeah, that's all right. Then what we have is 4156.84 at an angle, negative 0.13 degrees. So the magnitude of AB, the line-to-line voltage at the source, 415684 volts RMS. That's the answer. Now, the way we found it is because we have a single-phase equivalent circuit, we can then use it to find VAN, right? The voltage here from this to this, and then we use a voltage shift, which we've been doing. You can do that voltage shift between line voltage and phase voltage for delta. Usually we're talking about delta loads, but now we have delta sources. So you can use the exact same equation, whether it's at the source end or it's the load end, when you're shifting between voltages, right? Now, a little aside I want to point out to you. I don't want to go into too much detail, but I want to tell you, there's more than one way to solve every single one of these problems. I went back to the single phase equivalent and I showed you find VAN and then find this voltage drop and shift. That's totally fine. But there's another way to solve this problem. I'm going to go ahead and outline it for you. I'm not going to do it for you, but I'm going to show you that you can. You go back here to our little drawing of our delta source, right? We already knew what VBA is. We already know, or not VBA, we already know what the current VBA is. The current through this leg, we already know what it is. We calculated it for part B. It's this one right here. It's 0.69 amps magnitude at an angle of 16.26. That is the current flowing between B and A. That's literally the current here, right? The question says find the magnitude of the line voltage, meaning VAB, right? So if we already know the current in this leg of the triangle, and we want to know the voltage across this leg of the triangle, how would we do it? Well, we have the current here, and normally you would just multiply to get the voltage, but here we have a voltage source here, right? So what we do is we know the current going through this impedance. Notice this is not the transformed impedance of our Y source. This is our actual delta source. So this impedance in this triangle is actually this one up here, right? V between A and B, right? Like this one. So what we could do is find the voltage across this just by multiplying the current we know is in this leg times this. This is going to give us this voltage drop. And we know this voltage drop, so we could basically sum them together in the correct way to get VAB, and then you get the total voltage across the two things. If you were to get your calculator out and do that, you would find you get exactly the same answer doing it this way. So there's more than one way to do a problem. If you actually go through the trouble of calculating the current through one of those legs in the triangle of the delta source, and then later on it says find the voltage across the same leg of the delta source, then it might be easier for you just to use that previous answer and go here and do the same sort of thing. I encourage you to actually do that, because what you're going to find out is all this shifting that we were doing here that we had to do when we did it this way, it's actually already been it's already taken care of by what we've been doing in previous parts of the problem for this. So I'm not going to belabor it too much, but when you go and do it, you're going to see that the shifting that you did here is already done over here whenever you do the calculation. That's why it allows you to get the exact same answer. So really quickly, we want to recap, because this is our first, what I consider, real problem that we were going to use. So we have a delta source. First of all, we talked about the fact that it doesn't look like a triangle. So I showed you how you can, this is the top of the triangle, and we swing this, and we swing this, and basically it forms a triangle here. And we need to transform it into a Y source in order to model it as a single phase equivalent circuit. So we take the source impedance, divide by 3, and that gives us that. We take the source impedance, the source voltage, divide by square root of 3, and shift it one way or the other, and we figured out the phase sequence, so we shift it by positive 30 degrees, and we end up with a source voltage like this. This is an equivalent Y source. So when we model our single phase equivalent circuit, we use the equivalent voltage we calculated, the equivalent impedance for the source we calculated over here, and then the line and the load impedances are all given in the problem statement. So this is our single phase equivalent circuit. From that, we calculate the line current. This is the current that really is flowing through the A phase, through the line, into the load, and back around again, okay? From this point to the left, it's kind of a fictitious equivalency, but from this point to the right, it's the real circuit with the real current IAA flowing through it. Now, the second part of the problem was to figure out what is the line-to-line voltage at the load, VAB. So we treat it as any other three-phase circuit problem we've done in the past. We know the current, so we find VAN, the line to neutral, and since line to neutral and line to line are different for Y loads, we have to shift it. So we find VAN by just doing a simple multiplication with Ohm's law, and then we shift it. We have a voltage shift formula. Line voltage is square root of 3 times the phase voltage with a phase shift, right? So then we stick this all in place, and then we straight out calculate VAB. We throw away the phase because we're only asked for the magnitude, and that's what we get. Next part of the problem is find the phase current in the delta source. So what you want to do is you want to find the current circulating, or not circulating, but flowing in this leg of the triangle, because this is the A phase of the source, right? That's what you want to do. So the way you handle it is you basically say, well, I know that the line current is different than the phase current when you're talking about delta sources or delta loads, and I have a shifting formula for the current to handle it when I have to convert between line and phase current. And it literally is the line current is the square root of 3 times the phase current with a phase shift. So I know the line current, I put it in there, and I'm solving for this. So I divide by square root of 3, I divide by 30, which makes it negative 30 on the phase shift, and I calculate the line current, but I have to kind of keep track of it by reversing, just as a notation, the direction of the A phase in that triangle, and I get 0.69 amps. All right, now the last part of the problem says we want to find what VAB is, but at the source side, VA, the line, to B, which is not drawn here, the other phase of that line. The way we chose to do it is use our line current to find VAN. We had to do a Kirchhoff voltage loop to figure out by subtraction what the voltage VAN would be. Once we had that, we just stick it into here, and we just straight out calculate using the voltage shift formula. The thing I want to impress upon you that you're going to need to use in all of these problems is there's really only two real equations that you use in all of these problems. One of them we've been using for a really long time, and that is this one right here. Let me see if I can find a better example of it. Yeah, this one. There's a voltage shift and a current shift, right? You have a voltage shift where it's the line voltage, square root of 3, phase voltage with a phase shift. Now, it could be plus or minus, so we had to choose one in this case. That is what you do when you have for a line and either source or load where the voltages are different. In this case, they are. So we had to do a voltage transformation. We did it that way. That's a voltage shifting formula. Then we also have a current shifting formula when the current between the phase current and the line current is different, and that's the same thing. It's a line current square root of 3, phase current with a phase shift, but it's flipped over minus plus instead of plus minus. So that's what we had here. So notice that this entire problem really just boiled down to building our single phase equivalent circuit, finding the line current, and then either using voltage or current shifts to figure out everything else. And that's all you have to do. You just need to know when the voltage between line voltage and phase voltage is different, which is always in a Y load or a Y source. The line voltage and the phase voltage will always be different, so you use that standard voltage shifting formula we always use. And you have to know when the currents will be different. The currents are different between line and phase in delta loads or delta sources. So that's why we have to use that guy there. So you use a voltage shift sometimes and a current shift sometimes when those quantities between phase and line, either line current, phase current, line voltage, phase voltage, are different. So make sure you understand this, solve it all yourself, including, I would recommend the alternative way of finding that VAB quantity that we talked about. And then follow me on to the next section. We'll continue getting practice with three-phase circuit problems.